Hello everyone, welcome to my videos on elementary differential equations. This is video number 13 for chapter 2. In this video, we continue our discussion on modeling. Let's look at modeling type number 2. These are problems related to interest rates and mortgage problems. Okay, let's take an example. Let's say you start an IRA account at age 25. And suppose that initially at the beginning, when you open the account, you deposit $2,000. And then afterwards, each year, you contribute $2,000. Assuming now the interest rate is a very optimistic 8% annually. But we assume that it's compounded continuously. Now we wish to find the total amount in my account after 40 years. Okay, so to solve this problem, we would like to set up the model first. So let now S, a function of t, be the amount of money in my IRA account after t years. And recall the assumption here. We assume it's compounded continuously. Okay, so that means the rate of change, ds dt, we can talk about this instantaneous rate of change now, would be the rate it changes every year. So what happens every year? So every year I will receive an interest rate, 8%. So that will give me this term, 0.08 times S. And in addition to the interest rate increase, I'm also putting in $2,000 every year. So I have plus 2,000. So that will be the rate of change to my account every year. And then I assign the initial condition. So initially at T0, when I open the account, I put in $2,000. So S0, 2,000. Okay, now we see that we have a very nice first order linear equation with the initial condition. So we already had discussion on how to solve such problems, and the standard method is the method of integrating factor. So I will go through this, not talking in too much detail. Okay, so first we move this term to the left, write it in standard form, and then we realize P is this constant here. Then we use the formula to find the integrating factor, which integrate this is just that function, so this gives me an exponential function. And then we use the formula to find the solution. So the solution will be mu to the power -1, which is here, and then we integrate the right-hand side, 2,000, the g here, times the integrating factor, and dt. And then this is an indefinite integral, and we can work out this integral, and we'll get this. It's just the exponential function. So what I get is the exponential function and divided by its coefficient and times 2,000, which is a constant. And then remember to add the integration constant, the arbitrary constant. And then we can distribute the exponential function in, and this will cancel that. So I get 2,000 over -0.08 and plus c times that, the exponential function, which is here. Okay, and then we can calculate this fraction here, and we get -25,000 plus the constant c times the exponential function. Okay, so here the c is currently unknown, and which would be determined once we inserted the initial condition. Okay, so here I put the general solution form from the last slide, the last line with the C, and we put initial conditions. So S at 0, setting t to be 0, I will get the constant plus C times e to the 0, which is 1, and that has to be 2,000. So this gives me the C is 27,000. Okay, putting the C back, we can write out the solution. So this is the solution. So the solution means that at year t, the value of this expression will be the amount of money I have in my account. Okay, so to determine how much money there is after 40 years, we just need to evaluate this expression with t equaled 40. So as 40, you just plug in 40 times 0.008 is 3.2, and one can hit the calculator and figure out that this is the amount, $637,000. It would be interesting to compare this total amount of money you have in the account to the money you invested, that is the total amount of money you put into the account. So that's an easy computation. So we initially put 2,000, then we added 2,000 every year. So for 40 years, that product gives you the amount. And add up, you see that you invested total $82,000. But after 40 years, and you will have $637,000 in the account. Okay, so it's a big change. And as you are thinking, yes, this is caused by the very high interest rate for the problem, 8%. You're welcome to run the same thing with a lower interest rate or even higher to see how it dramatically changes this number of. Okay, so in our next example, we will look at a mortgage problem. So let's assume that you are a home buyer and you can afford to pay $800 per month as down payment in your mortgage. And let's say interest rate is given R annually, but we assume it's compounded continuously. And then the mortgage term is for 20 years. That means after 20 years, you have to finish your payment. And now we want to ask you to determine the maximum amount that you can afford to borrow with the interest rate R. Once that expression is found, which would be expressed in terms of R, we calculate this amount for two different interest rates, and we wish to observe the difference. Okay, so we need to set up a mathematical model for the problem. So the quantity that we are studying here, let's call it Q, a function of t, will be the amount that you still own. That means the principal in your account after t years. Okay, so how does that quantity change? So there are two factors affecting this quantity here. One is the interest rate. If you don't pay back, then the principal will grow at that rate. So dq dt has a positive term r times q that growing at rate r. But you are doing something to reduce it. So every month you pay $800. So since time unit here is year, then every year you are paying 800 times 12. And that's what you put in to reduce the principal. So this will be the differential equation that describes this quantity Q. Now, however, for this problem, the initial condition is not given. And in fact, the initial condition is something we wish to find. But we do know the terminal condition. That is, after 20 years, I must pay back everything. So that means if you solve this equation, and then Q evaluated at 20 must be 0. And as we know, the solution for this equation will contain the quantity Q0. And then using this relation, we can find the Q0. Okay, let's solve this equation, writing it in the standard form, moving the r to the left-hand side, and then p is just negative r. We quickly get our integrating factors and put the factor into the solution form. Mu to the negative 1, g is here, and then mu, and then we integrate. Okay, so this integral, you work it out, and you get this term here, and then there is an arbitrary constant. And then we can distribute the exponential into both terms, and then the first one becomes a constant, just this number divided by r, and the second one is a exponential function, c times e to the rt. Okay, now we need to find the constant c. So usually we find it with the initial condition. But here we don't have initial condition, but we have the terminal condition. Q20 equals 0. We see that we can impose this on the solution and determine the value c. So that's what we do. Calculate Q20, set t to be 20, then I get this expression to the 20 equals 0. So here in this expression, everything is given and c is the only unknown, and we can solve for c, and we get c is negative this number, and then divided by this exponential. Now we can put the c back into the solution, just put in the constant, and we rewrite it. So this solution is the principal on the account at year t. And also we know that this solution satisfies that the terminal condition, and that is q at 20 equals 0. And now we can use this to find the initial amount that we could borrow that will result in a completion of our down payment for 20 years. That is, the initial amount is simply Q when t is at 0. So plug in t equals 0, we get this constant, and e to the 0 is just 1. Okay, so we basically get this expression. And of course, it depends on r, which is the interest rate. And we can make it a bit simpler by taking out the common factor, and then we'll have 1 minus e to the, let's write it to be the negative power 20r. Okay, now let's check exactly how much you can afford to borrow with the specific interest rate being offered. Let's say if r is 5%, that is 0.05, then Q0 would be just putting r to be that number, then we get negative 1 here, and you hit the calculator and you find out that it's $121,000 something. Now let's look at the case where the interest rate is higher, let's say 9%. Okay, let's put it in 9 here. We get negative 1.8. And then use the calculator to compute that, and we see that we can afford to borrow about $89,000. So looking at the difference of these two numbers, we are not surprised to see that with a lower interest rate on the mortgage, we could afford to borrow more. And with a higher interest rate on the mortgage, we could afford less. Okay, so let me put some remarks on these interest rate, particular on the compounding of interest rate. So let's consider R to be the annual interest rate. That means for the time t, the unit is year. And then let Q0 be the amount of deposit initially. So we are considering only an account that you deposit money and you gain money with the interest rate. Okay. So let's say if the interest rate is compounded continuously, then we will get an exponential growth model. And then after t years, the solution is an exponential growth. So Q of t will be Q0 times e to the RT. But in reality, the bank does not do that. They do not compound continuously. So let's consider a few different situations. Let's say, what if it's compounded quarterly? How do you compute? Well, if you compound it quarterly, let's call this quantity Q4, means 4 times a year. So how do you compute? So, okay, so you have the initial amount, then every year you compound it 4 times, and then so in the year it's 4t times you compound, and then each time, because it's quarter, so the quarterly rate would be R divided by 4, since R is an annual interest rate. So it's R over 4 here, but you do it 4 times and then times t. Okay, so this will be the amount you will get. And let's see if we compound it monthly. That means and it's a similar calculation as we did here, but we will cut the time year into 12 intervals, and then the rate here would be R over 12 when you each time you compound, and in the year we compound it 12 times. Okay, so we denote this by Q12. So this will be what you have in your account after time unit t. And let's assume that it's compounded even daily, so 365 days in the year. And so we see that it's a similar thing we have to do here. Then the daily interest rate is R over 365, which is much smaller, but it's compounded 365 times a year, so you get this factor. So which do you think is the best? Quarterly, monthly, daily, or compounded continuously? So let's see. So one can show that, in fact, we have this inequality. So sorry, that should be a little t. That is, we have this inequality. If you compound continuously, your quantity is bigger than, strictly bigger than if you compound daily. And that is strictly bigger than if you compound monthly, and that is strictly bigger than if you compound quarterly. Okay, so let's do some computation. Okay, so let's say you compound n times in a year, and then you know your amount in the account would be, let's say initially you put in 1 unit of money, so it will be 1 plus R divided by n, because that will be the rate when you compound, but you do n times, so it's 2 to the power n times t. Okay, so we can expand this expression by the binomial formula, which is just a Taylor expansion. So if we expanded that, and then we have a series. So the first term is 1, and the second term is this constant times that, so n times that, and the second one is a half times nt, this number here, and then nt minus 1, and then square of that, and then the next term is nt, and then nt minus 1, nt minus 2, and then the third power. And you see the pattern clearly, and this is an infinite series. Okay, so we can simplify a little bit each term and write out. The first term is 1. The second term, the n cancels the n. I'll have rt. And in the third term, I have an n, and cancels one of the n here. And then I join rt together to the power 2. So I took an n here, but then I need to divide it by an n in the denominator, so that this expression equals that expression. And for the third term, we do a similar trick. Sorry, a typo, that shall be a 3 here. And we write rt to the cube, taking 1t here, meaning we have to divide the 2 t's in the denominator, and then n cancels the n to the one of the n to the third, so I have n squared in the denominator. Okay, so the reason of this manipulation will be clear very soon. So now let's compare, or let's first write out the Taylor expansion for the exponential function, which would be the solution where we compound continuously. So for the exponential function, I will get 1 plus rt plus a half rt squared plus 1/6 rt cubed, and so on and so forth. Infinitely many terms. And now, since we know a priori that both of these series, they converge, and we wish to know which one is bigger, then we can just compare them term by term. And if we compare qn with q, we see that 1 equals 1, rt equals rt. The first two terms gives me nothing. But if I look at the third term here, and it's this expression is here, but this term contains this fraction, nt minus 1 over nt, which is strictly less than 1. So this term is smaller. And look at the third term. You see that I have an additional fraction, 2 fraction terms here, and both are less than 1. Then this is strictly less than that. Therefore, we can conclude that the sum of the series is strictly less the sum of this series. So we have this inequality. Now let's look at qn for different values of n. Let's say I have 2, one is n, one is m there, when n is bigger than m. So how does each term behave? Let's look at it. The first term, second term does not depend on the n. And then the third term, yes, we have this fraction term here. And here we see that when n gets bigger and bigger, this approaches 1. When n gets smaller, this quantity becomes smaller. Okay, and then look at the next one. These two terms, they behave in the same way. When n is bigger, and it's bigger, it gets closer to 1. When n is smaller, and then these two quantities are both smaller. So this term also becomes smaller. Therefore, we can conclude that for two different values of the integer, and let's say n and m, if n is bigger than n, then the series converges to a larger number. So qn is bigger than qm. Okay. And since they all converge, and we also see that in the limit, when you take n to be bigger and bigger, then the Qn quantity here will converge to the quantity Q. Okay, so next time if you go to a bank and deposit money, you would like to choose the option that they compound more frequently because of this inequality. Okay, so banks make money by compound less frequently. Okay, so hope you like this video and feel that we are smarter, and when dealing with bankers we have some insider mathematical information on how certain things work there. And that's all I want to say for these money type problem. And next time we will go into another type of modeling problem, namely the mixing problem. Okay, so hope you enjoyed this video, and I look forward to seeing you next time. Bye-bye.